Hello, so in this tutorial we're going to be talking about confidence intervals. We're going to take it sequentially. First of all, what do we mean by a confidence interval? Because I don't really want to start talking about what conditions we need for a confidence interval before talking about what one is. So we're going to talk about that, so we've got to be clear where we're heading for, what the basic idea is. Then, quite importantly, under what conditions do we need to hold in order to work out a confidence interval? I probably ought to be a bit more specific there. I should probably say using standard normal distribution. Standard normal distribution. There are other conditions, there are other techniques we can use when these conditions don't hold, but that they're off the OCR A-level course, A-level Further Maths course, so we don't need to consider them, although they are on other courses, for instance AQA I think, but we may mention it. I may mention what techniques we would use, but we won't actually go into any detail on that because it's not on the course. Then the next thing we're going to look at, once we've talked about the conditions we need to hold for us to use a standard normal distribution, then we'll do some examples and talk about how we actually do it. Okay, so that's where we're heading. Let's just take that board down. And here we go. So, what do we mean by a confidence interval? Well, let me fast forward to an example we're actually going to do in one of the examples when we actually start working out. You've got 64 sweets and you weigh 64 sweets from a larger sample of sweets from a manufacturer. And they weigh 64 of them and weighs 0.932 grams, say. So in other words, that's our X bar. Remember, X bar is the symbol we use for the mean of a sample. And we use mu to represent the mean of the population. Now, the thing is here, we don't know mu, we only know X bar. We picked 64 sweets and we found the mean of them. Now we could say, well, that means that the mean of the actual population is likely to be close to 0.032 because the sample size is 64. But the question is how close and how confident are we? So that's basically part of the idea, but let's just unpick that a little bit more. Interval, in a mathematical sense, it has a specific meaning, and in a statistical sense, it basically means a range of numbers. So for the interval we're actually going to find in the question here, I think is 0.900 to 0.964. So in other words, we work out that we're confident that the actual, so put mu there, the actual population lies between those two numbers. I should probably say quite importantly here, how confident are we? And that's the point. We always, a bit like when we do significance tests, we need to talk about how confident. And what we're going to talk about here is the 99% confidence interval. So in other words, only 1% of the, if we take all the possible samples of 64 of the whole population, only 1 in 100 of them is not going to be caught in this interval. Okay, so we're 99% confident because of our sample of 0.932 that our actual population mean lies between these two numbers. And we can look at this graphically. Suppose we have an actual mean there, and we were to take samples, and there's one sample which gives an interval like that, it catches the mean. Another sample like that, another sample like that, say, another sample like that, another sample like that, and then once in a while, maybe once in 100 times here, your sample doesn't, and your confidence interval that you've worked out as a result of that sample doesn't kind of capture the mean. But it all depends on how confident we want to be. If we talk about a 99% confidence interval, that will happen only 1 in 100 samples of size 64. that we work out. So we've only got 1 in 100 chance that our mean doesn't lie. Actually, our mean doesn't lie within those two values. Okay, so now let's move on to what conditions need to hold in order to use this technique that we're going to cover using the standard normal distribution. Well, let's just split it into two things. Let's just see if the sample size is large. Then we've covered the central limit theorem. We don't really need a lot. This technique would be used in so long as it's not a particularly unusual distribution, which is no reason to believe the weight of sweets or the examples we're going to do is. Then we can pretty well, so long as the sample size is large, it doesn't even matter if the parent distribution is normally distributed, because the central limit theorem can be applied. So if parent distribution is not normally distributed, distribution can't assume to be normal. Be assumed to be normal. Okay, so that's the first thing. I suppose we ought to draw a distinction between if the variance is known, then we're going to use Z is equal to our sample take away the mean divided by, we're going to use that which we've seen before when doing hypothesis tests and various things. We use that and manipulate that and basically make mu the subject to the formula of that, but we'll come on to that. If the variance is unknown, I suppose the first thing to say here is it definitely is an approximation now, but it's still, so long as the sample size is large, the central limit theorem can still be applied. But if you have to calculate an estimate for the standard deviation, then we would use that. In practice, there's not going to be a big, if the sample size is large, there won't be a big difference between the unbiased estimator of the standard deviation, whatever the using sigma would be. But if we've got sample, we should always use S as a matter of principle, really. So we use S, the sampling standard deviation, if the variance is unknown. Okay. But if the variance is known, which it will be in many cases, well, in many questions you'll come across, it will be. In actual fact, it's a bit of a moot point, because many situations in the real world, that won't be the case that the variance is known. Okay, so so if the sample size is large, then we're pretty okay. We're pretty okay. It's just which formula to use, depending on whether the variance is known or the variance is unknown. So we'd use the population. We probably know the standard deviation, so we would use that. But if we don't need to know the standard deviation, we use S as an estimator for it and use that formula instead. Okay, so that's large sample size. Let's talk about small sample size. Okay, so if it's a small sample size, then first of all, the parent distribution needs to be normally distributed. So we can't use the central limit theorem for small sample sizes. So parent distribution must be normally distributed. Right, so let's just, and then if the variance is known, then we can use z is equal to x bar minus mu over the standard error as before. Okay, now if the variance is unknown, which again in practice it will be, unfortunately, or fortunately, the distribution is not, this statistic here is not normally distributed, and that's where we would use your t distribution, which isn't. If you're doing OCR, which my students are asked, if you're doing OCR, isn't part of the course, but it is on other boards. So if the variance is unknown, small sample size, even if you've got a normally distributed parent population, this statistic here won't work, not accurately, because this is not normally distributed. If you're using S as an estimator for the mean, it doesn't work. So you end up with this other thing called the t distribution, which won't be covered in this video. Okay, so now let's get down into the nitty-gritty of how we actually calculate a confidence interval. Just a reminder of what one is. A confidence interval is an interval in which we infer with a certain level of confidence a population mean to lie within as a result of a sample mean. That's basically what we're doing. A bit of a mouthful, but that's basically what I've just tried to build up to previous to this part. Now we need to work with this thing called the Z distribution. That's what this video, with all of the methods we're going to do here involve basically referring back to the Z distribution. So we need to actually find the appropriate values of the Z distribution. So for example, if we're 90%, if we want a 90% confidence interval, we want 5% this side and 5% the other side, and the number there will be 1.645 and minus 1.645. 645. If we want to be a little bit more precise than that, which will of course narrow the interval. No, obviously, sorry, it will widen the interval. If we want to be 95% confident, then that's going to widen the interval because it's going to have a wider range between, in order to be that much more certain. We would want 2.5% each side. And that number is 1.960 or minus 1.960. You won't be expected to remember these. There's a couple of ways to get them, which I'll explain in a moment. If we want to be 98% certain, for example, that's 1% either side. Then the number we're looking for there is 2.326. And minus 2.326. And then finally, if we want to be 99% confident, then that's 0.5% on each side. The number we're looking for there is 2.576. Okay, now how to get these numbers? Well, if you're doing one of the A-level courses, the OCR, for example, the A-level Further Maths courses, you will find in the formula book probably some appropriate values, which will give you some of these. So, for example, the 90% one, we'd have to look for 0.95 because we've got 5% either side, so it's 1.645. Because we would have 90, we would need 95% below the 500, take away that 5% basically. And then we can see the 95% one, which is 2.5% each side, hence 0.975, 1.960. 98% one is not there. So we can talk about what we do if you don't want to use these tables or if you don't have access to them. And then the 99% one there, that's 0.995 because we've got 0.5% each side, so we've got that one. Okay, what to do if you either don't want to actually look at the numbers, or if you prefer to, or if it's not there, or if you prefer to use a calculator. Calculators will obviously work differently, but most of my students have got this one, the 991EX. So let's work out how you would do it here. You press menu and menu 7, and it's the inverse normal thing we want. So we can see there's a 3 there, and by default they normally put in the standard normal distribution here. And let's say we wanted that 98% one, which doesn't exist in the tables. We can just put 0.99 because it's 1% each side, so 99% below the positive Z value we're after. Press equals, and there we go, 2.326 is our number. We're going to do a few examples in a minute, but before we do, just talk about the general strategy. I've said that we want to transform to the Z distribution, which is Z, and we can use this transformation. Okay, well, let's just do it for a particular case. Let's say we wanted to work out a confidence interval for the 90%, which means looking at 0.95 on the tables, or putting 0.95 in your calculator, so that's 1.645. We'd have 1.645 equals to, let's use little x now for the particular sample that we've got, over sigma square root of n. We can rearrange that to 1.645 is equal to 1.645 n is equal to x bar minus mu, and then x bar is equal to mu plus 1.645 over the square root of n. But we want a confidence interval for mu, so we get mu equals to x bar minus 1.645 sigma over square root of n. But remember, this could be plus or minus. So here effectively we've got plus or minus here, and here that means we've also got plus or minus here. And although the minus signs, we could write it that way if you want, the plus or minus sign swap over, that gives us our confidence interval for the upper one being the positive and the lower one being the negative. Okay, and obviously we're going to change those numbers for our appropriate confidence interval that we're looking for. This would be for 90%. Okay, not particularly high level of confidence, so we're going to have, for such a high level of confidence, we are going to have quite a we can have put in quite a narrow interval in that case, but we can't be that confident about it. So it narrows the interval because the confidence level is relatively lenient, if you like, for want of a better word. Of course, so we can change the number. So our confidence interval, let's write it like this for the different numbers. For example, that would be, corresponds to the 4Z values I had above. So we've got our 90% here, we've got our 95% here, and then we've got our 98%, which we note that they don't actually have in the tables, so you'd have to use your calculator for that one. And then your 99%, which would be 0.5% each side from there. So you might, I mean, a lot of textbooks encourage or whatever just using this as a formula, but I must admit I tend to go from scratch, maybe because I don't do stats that often, that I tend to kind of just always remember this transformation and just know the idea of it, the process that we're going through, rather than thinking about the formula, because it's quite a lot to take in. Okay, let's do an example, or a few examples now, and then hopefully we're okay with confidence intervals. Okay, so let's just do this example here. Let's rub that out for a moment. Right, so we've got a machine cuts metal tubing into pieces. It is known that the length of pieces have a normal distribution. Okay, and that with standard deviation 4 millimeters, which means the variance of course is 16, but after the machine has undergone a major overhaul, a random sample of 25 pieces is found to have a mean of 146 centimeters. Assuming the overhaul has not affected the variance of the tube lengths, determine a 95% confidence interval for the population mean. Okay. So before I do the question, let's just think back to some of the points I was making before. Can we use a Z distribution? And we can use a Z distribution here. In fact, we should definitely use a Z distribution here, because the normal distribution, it's known that the pieces are normally distributed. There's a relatively small sample size on the dodgy side if you needed a large sample size of 25, but so long as the parents distribution is normally distributed, and here's the thing here, and the overhaul is not, the variance is known, the variance is unchanged, so the variance is known. So we've got, even though the sample size is relatively small, getting, we really want to be over 30 to be considered large enough. So, but it's fine so long as we've got a normal distribution and we have a known variance, and the variance is given here. Well, standard deviation, therefore the variance is given. So we can use the Z distribution. We want a 95% confidence interval. Okay, so we can either look at the numbers in the tables, or as I showed you before, show the number in the calculator. So the number we're looking for 95%, as demonstrated earlier, is 1.960 or minus 1.960. Okay, so what we tend to do is actually write that in to our distribution. Say formula really, so we can just say a Z distribution, which is our normal distribution with mean 0, standard deviation 1. We know from this, either we've worked it out using the calculator, or we've worked it out using the tables. We know that 0.196 lies between, and 1.96 lies between, the probability of it lying between those two values is equal to 0.95. Okay, so basically we use a Z value, or 1.96 we know is our Z value, plus or minus 1.96 we can put into the transformation, which is x bar minus mu over sigma square root of n, which basically means we can write this mu as a subject to the formula here. So we have P is equal to, and we're going to now put this into the formula, minus 1.96 less than Z, which is equal to x bar, and we're told that x bar is 146, minus the mean, which is what we're trying to get the confidence interval, divided by the standard deviation, which is 4, and the sample size is 25. So all I've done is rewrite this with the transformation in. Okay, so now we can let mu be the subject to the formula. Now I wouldn't worry about trying to faff about with inequalities, because there is something strange that happens with the plus and minus signs. Just rearrange this if you can't remember how to do it. Rearrange as I did above in here, or just do it in your head. Just rearranging that gives us that mu must lie in between 146 minus 1.96 times 4 over the square root of 25, or 146 plus 1.96 times 4 over the square root of 25 equals to 0.95. So now we can just go to our confidence interval, work those out. So the 95% confidence interval for mu is going to be equal to, just working these two numbers out, that's equal to 144.4 approximately, and 147.6. So we don't know that the mean lies between those two values, but we can be 95% confident that it does. So 1 in every 20 will have missed it, but most of the time, 95% of the time, the actual mean, which is unknown, lies within that interval. Okay, let's do another example. Same idea, but just want to do a different example with a slightly different context, and just to kind of talk about the issues about when we can use this technique. Okay, so here's another example. Now, first of all, things to note is, can we use Z? And the answer is yes, because the sample size is large. So even though we don't know what the standard deviation is, even we're given the sample standard deviation this time. We don't know what the standard deviation is. Neither are we given whether it's normally distributed. But this is okay, provided the sample size is large. Okay, so that's fine in this case to use the Z distribution. And again, it's the only thing we could do. We're basically using, again, something that I go on about a lot, the central limit theorem. The basis that if the sample size is large, even if the parent population is not normally distributed, we can use the normal distribution because the sampling distribution will be approximately normally distributed. Okay, so let's just first of all look at our Z value. Okay, always go back to the Z value. You're going to find this number from the tables. Hopefully rewind a little bit if you want to see how to get this number. So 99%, we're going to put 0.995 in the calculator, or we're going to look in the tables. 99%, the appropriate Z number we need is 2.576. Okay, 2.576, or minus 2.576. Okay, so what we tend to do is probability that the Z lies between these two values equals to 0.99. Yeah, that's what we found out from there. So then we can use the transformation that we know that the Z is equal to x bar minus mu over sigma square root of n. Now say, just rearrange separately if you need to, don't necessarily need to put into the inequality, in fact I wouldn't. So you can then say plus or minus 2.576 equals to x bar minus mu, and x bar is equal to 0.932. Take away the unknown mean, divided by, now this is an estimate, so we can use, although it's only an approximation or an estimation, we can use this if the sample size is large. So that's important. Size is large. Okay, so that's divided by, we're given the standard deviation, the mean mass, and the sample standard deviation is 0.100, which gives us an estimate of our actual standard deviation for the population over the square root of 64. And you can rearrange that and you'll get mu is equal to 0.932 plus or minus 0.100 over square root of 64 times by 2.576. Okay, you don't have to do that. You might just be able to hardwire to the straight thing, but all I would say is I would advise trying to manipulate the inequalities and all that. You could just do this calculation if you want as a thing, and then just stick into your inequality, your probability statement based on the Z distribution, just stick it in there and you'll be away. So that gives us mu is less than 0.932 plus or minus, I've got that space here, plus or minus 0.100 over the square root of 64, 2.576. It's a mu, which is less than, so it's not plus or minus this time, we're looking at the negative, of course. And the upper bound is 0.932 plus this standard error, which we've times by the appropriate Z value. Equals to 0.99. So that gives us the probability that mu lies between, and I think the numbers now comes to 0.900 to three significant figures, mu, and 0.964 equals to 0.99. So that means the 99% confidence interval for mu for the mean, the population mean, do make the fact, don't just too many students just write a load of numbers and don't kind of conclude. This is the business here. This is the business end of what we've got. That's the answer. Okay, the rest is a little bit of fiddling around really. How you just have to feel your own way with this, but it's got to make sense to you. I always say that with any part of mathematics or any part of statistics, which is why I like to start off with Z, and rather than just remember a load of formulae parrot fashion. Okay, let's do one more example, and then I'll talk about an example of when this can't be done. Right, in terms of the conditions, this is similar to the example before. We're basically using the central limit theorem again, really, because we're not told that the distribution is normally distributed, but because the sample size is 100, we're okay to use a central limit theorem. And so it's similar, central limit theorem, even though it's not normally distributed, it's all okay. Now, the only difference is that they've given us summary data. So we need to work out estimators for the mean and the standard deviation. So the unbiased estimator, a value of x bar, is obviously sigma x over n, which is equal to 1,72800 divided by 100. So it's obviously equal to 1728 centimeters. Okay. I've added an extra 0 in the data there because 17.28 meters is an unlikely height, so I think that's what I meant. Okay, so now the standard deviation. I wanted to actually, perhaps we don't make enough emphasis on this on the A-level course, this thing about estimators and the difference between a population standard deviation and a sample standard deviation. And if there's enough demand, if people request it, I will do a separate video on this. But basically the idea is that you've got, for a population standard deviation, if it's a population, if it genuinely is, or variance, we can use this formula. I tend to use this formula, okay, if it's a population. But in many cases, we don't know what the actual population is. That's the whole idea. We certainly don't here. We've got a sample, and it's difficult to prove, but possible. And it isn't that mind-blowing. It is something I can do using expectation algebra if you want, but I'm not going to here. Is the estimator for that is an estimator for the standard deviation, which is what I use, is this ratio times by the population standard deviation. So and I think the formula is given in the formula book for the estimator, unbiased estimator of a standard deviation. I think it's given as something like this, over n minus mu squared, or it might be given as sigma x squared, or they might stick an f in there as well. I'll just put up what they've put in the formula book now. I'll just paste it in just for clarity from the OCR textbook. Okay, so there it is. It's actually worth looking at other stuff. It tells you basically tells you the central limit theorem here, although it doesn't call it that. It also gives you the transformation function to the standard normal distribution. So, and quite pleasingly, it quotes that formula, which I prefer to see it in that way. Some of you will see other versions where it gets multiplied out, because if you multiply this out, you can see a similar formula where the n cancels, and you have the n minus 1, and then you can have something like this, which does involve a little bit less calculation, over n minus 1, n minus 1, so, or something like that. I don't know exactly if it goes like that, but something like that, n minus 1. See various versions of it, but actually I much prefer to see this is the calculation we'd do if we knew the whole population, and this is the adjustment for the fact that it has a sample. And so there's a relatively it's not straightforward, but there is not much beyond what we need to do to actually prove that this is a unbiased estimator of the population standard deviation. So for those who just think, oh come on, just tell me when to use this one and when to use this one. Well, basically, if it's a sample, which you will, in further maths, it always virtually will be, won't it? It'll be a sample. You're either working out a confidence interval or doing a hypothesis test. If you're basically estimating the standard deviation using this formula. In the straight single maths A-level course, it's not a thing at all, this formula, and you would always probably be using this. Okay, so let's just get rid of some of this stuff. So rejigging this a little bit, we've got this is equal to sample size is 100, so 99 sigma x squared, so that's 2,995,400 over n, which is 100. Take away the mean squared, which is 172.8 squared. Okay, and that comes to, remember this is the variance, that comes to 95.11. So now we're talking about the confidence interval. We want a 98% confidence interval. So, and looking back, these numbers aren't in the tables given in the formula book, so you have to use a calculator. Rewind to the point where I did that, if you don't know how to do that. We've got 1% either side for it to be a 98% confidence interval. And so we, the number that we're looking for will be 2.326, and obviously minus 2.326. So let's write that out as a statement that is about z. We're basically saying that the probability that z lies between minus 2.326 and positive 2.326 equals to 0.98. Right, okay, so that means that we can do our transformation. So that's our x bar minus mu over sigma n minus 2.326 and 2.326. And if you want to do the algebra separately, or if you can do it in your head, whatever, just don't try and mess around with the inequalities. So if you wanted to, you could do plus or minus 2.326 equals to x bar minus mu over sigma n. Oh, and we do know sigma and n. And rearrange if you wanted to do that separately, but I'm just going to do off the bat straight here. So let's write in our thing with our values in 2.2326. This then the x bar that we found, the x bar which we found, which is 172.8. The estimator for the mean, the sample mean, is 172.8. Take away the unknown population mean divided by, there I probably should have put S here because we're using S as an estimator for the standard deviation. So that would be 95.11, but it's a square root of 95.11 because this is the variance. This is so many times I see students mixing things up with variance and standard deviation. Think very carefully. This is the variance, so the standard deviation is the square root of that. And we've got the square root of n, and n is equal to 100 in this case. So we actually have the variance, 95.11, divided by 100. And that's lying between these two values, equals to 0.98. So now making mu the subject of that formula, you might choose to drop the p at this point because it's the interval we're interested in, but I just like to write it because it kind of reminds me what I'm doing sometimes when you've got a few things to think about. So that means rearranging that, we're going to get that mu greater than this estimator, our value of x bar, minus 2.2326 1.26 times by 95.11 over 100 is our lower bound, and the upper bound for our interval is 172.8 plus this 2.2326 times by our standard error, 95.11 over the square root of 100. Okay, and working that out, that gives us mu lies between 170.5 and 175.1. Let's write as a probability statement at this point and then conclude. So that means that the 98% confidence interval for mu is greater than 170.5 and less than 175.1. Okay, so that is basically it. There's a 2% chance that mu doesn't lie within that interval, but we're 98% confident that it does. Okay, so that's nearly it. It's certainly it for all of our examples. I just want to, for those who are familiar or interested in this thing, the t-test or student t-test, I'm going to give you an example of where we can't do this method. And here we've got a sample size which is just too small, and even though the parent distribution is normally distributed, because the sample size is too small and we don't know the population standard deviation, we can't use this method even though it's normally distributed. We know that much. And there, the method there is the t-test or t-test or t-test, or using the quite name, I think, for it, the student t distribution. It's not on the OCR course that many of my listeners are doing, but it is on others. I think it's on AQA, I think it's on MEI Major, and it's on the Edexcel stats, one of the advanced stats courses on Edexcel, but it's not on OCRA. So unless I get any special request to talk about or do that example, I won't. I just thought we do need to know that when you can use the normal distribution, the Z function, to actually work out a confidence or interval, and when you can't. And there's an example you can't because the sample size is too small. Okay, so it's been quite a long tutorial. I hope you found it useful. If you're one of my students, if you could continue the exercise on OneNote at this point, that would be brilliant. Anyone else, if there's any questions, do ask on YouTube. I may have time to answer. Thanks very much. Bye.